Okay, welcome to welcome to video class number 15. In this session we are going to deal with the discrete time Fourier transform. Fourier transform. Now, in the last video we have seen that a particular discrete time signal, say x of n, can be periodic or aperiodic, right? Now, if it is a periodic signal, that can be represented by DFS or discrete Fourier series, as we studied in the last two videos. Now, there is as in a continuous time aperiodic signal, this aperiodic signal cannot be represented by its corresponding Fourier series, because this is not periodic. But there must be some Fourier transform corresponding to this aperiodic signal, and so that Fourier transform we call as, since it is the Fourier transform of a periodic discrete time signal, we call this as DTFT. So along with this, I am also introducing another term called as DFT. This is called as the discrete Fourier transform. Discrete Fourier transform. This is called as discrete time Fourier transform. So I will be explaining, even though DFT is beyond the scope of our syllabus, it's not in the syllabus, we just need to study only about DTFT, but still I'll give you an idea about what DFT is. Anyway, you should understand these two are different, and in some of the textbook along with the DTFT chapter also you have DFT. Don't misunderstand, and it looks alike. Many of the portions looks alike, but you should not be confused when studying. You should see that the transform you're studying is DTFT, not DFT. This is discrete time Fourier transform, while DFT stands for discrete Fourier transform. I'll be explaining it later. What is this DFT? Anyway, our subject is discrete time Fourier transform, that is DTFT. So as I have taught you in this, when we dealt with the aperiodic signal, that is when we dealt with the continuous time signal. So suppose you have a periodic signal like this, right? And it goes on like this. Let it be Goodiston. And it goes on like this. So you will call this as your, say for example, this has your n minus 1. This is your n, and so let it be some value up to n. So you can say that up to this sample you have n samples, and this n samples repeats. Now what happens when you extend n to infinity, this point to infinity, meaning you have only these samples. So what will happen to this x of n? Say let us call this as a periodic signal, so let's call this as xp of n. So what happens to the periodic signal when n is extended to infinity? As we studied earlier, this becomes your x of n, or this is a aperiodic signal. Right? Now, in order to study the frequency spectrum of a aperiodic signal, we study, or we use the tool discrete time Fourier transform. Now, the condition for a signal to have the discrete time Fourier transform is, what is the condition? So first of all, let's see the condition for x of n to have what? DTFT. The condition is nothing but if you summate x of n, we do not know from where to where, so we simply take n is equal to minus infinity to plus infinity. When you summate this, that is the magnitude of this has to be less than infinity, or this has to be a finite value. Okay, so this is the condition, a sufficient condition for the existence of DTFT for a periodic sequence x of n. Okay, now let's see the basic expression for this. Now, as I told you earlier, the Fourier transform is usually represented by x of e raised to j omega or x of omega, okay, or it is also equal to x of j omega, okay, and I mean, these are the ways you can represent a Fourier transform. And this Fourier transform is represented by, say, you multiply your x of n by e raised to j omega, e raised to j omega n, e raised to minus, okay, e raised to minus j omega n sigma as n varies from minus infinity to plus infinity. Okay, now what is this omega? Omega is actually the discrete frequency, the frequency of a discrete signal. Okay, but now this omega is a continuous variable. This is a continuous variable. Okay, this is not discrete, only the time domain is discrete. This is just a variable, and that is a continuous variable. Say omega is of the form 2 pi by n. Okay, 2 pi by 1, 2 pi by 2, 2 pi by 3, all these things are a continuous signal. This is not discrete in nature, right? Now this is, so that means this signal is going to be this should be a function of omega, or x of omega is written like this, where omega is a continuous variable, so it's a continuous function. So what is the result? When you represent any signal, any periodic signal by discrete Fourier series, that is discrete in nature. What about DTFT? DTFT is continuous in nature. That is the first point that you should note about this. Okay, in the continuous time signal also we have seen the same thing. In the periodic continuous time signals, the Fourier series is discrete in nature, that is Cn, while its corresponding CTFT is continuous in nature. So similarly, this is also continuous in nature. Okay, now why omega is said to be continuous? All of you listen please. So you may be having a doubt why omega is, since it is called as a DTFT, even though it is called as a discrete time Fourier transform, it means only the Fourier transform of a discrete signal. That is why this Fourier transform is called as discrete time Fourier transform. It doesn't mean that this is discrete in nature. This is continuous. I will prove that. Now what is this omega? Omega is actually 2 pi by n, okay, where n is the period. We have already seen that a period is always defined for a periodic signal. Now what is the period of, what happens to a periodic signal when n tends to infinity? That becomes an aperiodic signal. So you can say that for an aperiodic signal n is infinity. Even if it repeats only at infinity. You don't have any repetition in between. So what will happen to this? Omega is 2 pi n means it reduces to 0, right? So as n tends to infinity, what happens is this 2 pi by n becomes 0. That means this 2 pi by n represents what? Represents the spacing between the spectral components. That's what we studied in the Fourier series, right? You have a Fourier series, say Fourier series like this. This I have explained when during the continuous time as well. So this spacing is denoted by 2 pi by n. Now what happens as n tends to infinity? This spacing becomes closer and closer, and almost it becomes a continuous signal. So in that case, omega is a continuous variable. So Since omega is a continuous variable, this DTFT is a continuous function. Hope you understood that difference. You must clearly understand this. This is a very important idea. You need to understand this. Okay. Now, if there is an x of omega, then you can have, if you are given with the x of omega of a signal, you can find out the corresponding x of n using the expression. Okay, using the, so this is going to be, so if this is called as a DTFT, this is called as a inverse DTFT, right? Inverse DTFT. So what is this inverse DTFT? So you will be given with x of omega. We know that x of omega is what? X of omega is a continuous function. So definitely you need the help of an integral. Then so here you have used e raised to minus j omega n. So in order to find out the inverse, it will be plus j omega n. Then this is a function of omega, so you need to integrate this from d omega. And what about this? So this is equal to minus pi to plus pi 1 by 2 pi. Okay, 1 by 2 pi. Okay. Now you might have noted that it is not from minus infinity to plus infinity. We must have a reason for that. Now, when you try to find out the reason why this limit is not from minus infinity to plus infinity, but instead of that you are using minus pi to plus pi. What is the span between minus pi to plus pi? It is 2 pi, right? So that means this has got, it doesn't mean that after 2 pi there is no signal. No, it's not like that. Since it is the frequency domain of discrete time signal, already we have studied in Fourier series that the frequency also get restricted, or the frequency spectrum is also periodic. So you can prove that here also this x of omega is periodic. Okay. Now the next question is, if it is periodic, what will be the period? The period is equal to 2 pi. I am going to prove it. Now what is actually, if say a particular function, if it needs to be periodic, it has to be like this. You need to prove x of omega plus 2 pi is equal to x of omega. Okay. Now what is your x of omega? X of omega is, we have already written here, that is sigma n equals minus infinity to plus infinity x of n e raised to minus j omega n, right? So this will be x of, so what will be x of omega plus 2 pi? This will be sigma n equals minus infinity to plus x of n e raised to minus j omega plus 2 pi into n. Okay, now this will be sigma n is equal to minus infinity to plus infinity x of n e raised to minus j omega n into e raised to minus j 2 pi n, or this is equal to sigma n is equal to minus infinity to plus infinity x of n e raised to minus j omega n into what? This can be written as, cos 2 pi n minus j sin 2 pi n. Okay, sin 2 pi, any multiples of sin 2 pi will be equal to 0. Any multiple of cos 2 pi will be equal to 1. So this is equal to 1. That means this results in sigma n is equal to minus infinity to plus infinity x of n e raised to minus j omega n. What is this? This is x of omega itself. So we have proved that this DTFT is periodic with a period 2 pi, and because of that reason, when we find the inverse DTFT, we take x of omega, or we integrate x of omega along its period, and the period, okay, the total span has to be 2 pi, that is minus pi to plus pi, it spans to 2 pi. Okay, now let's do some simple problems on discrete time Fourier transform. Okay, the first question, it's always a simple. Find the DTFT of the following signal del of n. Do you know how del of n looks like? Del of n is, there is a difference between del of t and del of n. Del of n will be equal to 1 at n is equal to 0. This is not defined as a in a continuous time signal. It is defined as a value, as a signal having a value equal to 1 at n is equal to 0. But that's not the case with the continuous time impulse signal that we all know. I have explained it in detail while in the class. Now, how to use this? You can use this. This is the basic expression, right? This is the basic expression of DTFT, that is sigma n is equal to minus infinity del of n e raised to minus j omega n. But we know that this, from this figure, it can be easily understood that del of n is equal to 1 at n is equal to 0. That means this particular equation will be having only the value at n is equal to 0. The rest of all the values will be 0. So that means this expression reduces to, so at n is equal to 0, this exponential also becomes equal to 1. So that forms x of omega is equal to del of 0, and we know that del of 0 is equal to 1. So what is the implication of this? So the figure of x of omega looks like this, meaning it is irrespective of the frequency. Okay, irrespective of the frequency, or it will contain the frequency content of an impulse signal will be having all the frequencies starting from 0 to infinity or from minus infinity to plus infinity, having an amplitude equal to 1. So the impulse signal is a signal which consists of all the frequencies that you can imagine. Okay, so that's the implication of this x of omega, right? Now coming to the next signal, which is u of n, and we have studied in the case of a continuous time Fourier transform that u of t is not an integrable function, right? So we studied that u of t is not an integrable function. What's the meaning of integrable? That is, u of t, del of t from 0 to infinity is not going to be a finite value. So in this case, we also noted that for such signals you don't have a Fourier transform. But anyway, we managed to find out the Fourier transform in terms of, first of all, we represent this u of t in terms of Zignum function, and the basic step is, what we do is, even without representing it as a Zignum function also you can do this. What you need to do is, you must multiply that e raised to minus u of t by e raised to minus at limit a tends to 0, right? So that this is what is called as the limiting function. This is called as a limiting function. So when at the value of a, this signal has to be equal to 1. So effectively we will be finding out the Fourier transform. Now when you multiply u of t by e raised to minus at, this u of t becomes what? U of t becomes a time limited signal or a integrable signal. Okay, now exactly the same, u of n is also equal to what? When you add the sigma n is equal to 0 to infinity 1, it is going to be infinity. It is going to be infinity. It's not going to be less than infinity, meaning that this doesn't have any Fourier transform. But we can manage to find the Fourier transform by using the same principle. Okay, by multiplying u of n by a time limited signal. Okay, now one of the time, so this is not an integrable function, therefore the Fourier transform does not exist. So in a discrete signal, an exponential signal, you can think of an exponential signal like this. It's not, it tends to 0. A raised to n is an exponential signal, limit as a tends to 1. Okay, now here is it. So this is how it is. So what happens in a raised to n? So when you put a, this becomes equal to 1. Okay, just similar to when you put a is equal to 0, this becomes equal to 1. But effectively this signal converges this u of t, right? Similarly, when you multiply this signal by a of u of n, provided a must lie between 0 and 1, it is tending to 1, meaning a is less than 1 and it is getting closer and closer to 1. That, it can be viewed in that way. So if it is viewed in that way, then you can simply write the expression to be, so you are multiplying your u of n. This is actually 1 means it is u of n, a raised to n into u of n as a tends to 1. So you are multiplying this u of n by a limiting function so as to make this u of n a integrable function, that multiplied by e raised to minus j omega n. And if you can assume that these values lies in between 0 and 1, or in some other words it is close to 1 or it is tending to 1 from 0, means it will be having a less than 1 value. So in that context, limit a tends to 1 plus a into e raised to minus j omega a square into, that is the expansion of this. So n is equal to 0, 1. n is equal to 1, you have a into e raised to minus j omega plus a square into e raised to minus 2 j omega, and so on. Now, since there is a condition like this, if there is only a condition like this, that is this is actually what? This is actually a geometric progression, right? And if you know that the geometric progression having a common ratio r, if r is less than 1, you can write the sum to be 1 by 1 minus r. Okay, now what is r here? R is actually equal to a into e raised to minus j omega. Is it less than 1? If a is 1, it is not less than 1, but we are assuming that a is a value which tends to 1, meaning it can be a less value than 1. So that means a raised to e raised to minus j omega modulus is less than 1. What is the modulus of e raised to minus j omega? That is equal to 1. So in order to make this converging, you should multiply by a term which is almost less than 1, but it is close to 1. Imagine like that, so that it will be less than 1, you can write in this way. But there is a limit as a tends to 1. So and as you apply this limit, you will be getting a 1 by 1 minus e raised to minus j omega. So this is what I told you when we found out the u of t as well. I mean, in the strict sense, you don't have a Fourier transform for u of n as well. The reason is exactly as that of a u of t. U of n is not integrable, but you can make some non-integrable signals into integrable by multiplying a function called as the limiting function. Hope you understood about this limiting function that we used. That is this is the limiting function that we used, limit a raised to n as limit a raised to n as limit a tends to 1. Okay, now problem number 3. You have the problem number 3, del of n minus k. Okay, now this del of n minus k will be like this. So this can be called as this can be called as del of n. Okay, now what is this del of n minus 2 or n minus 1? So this signal gets shifted. So this signal gets shifted by 1. There's nothing like no. Okay, so this gets shifted by 1. So this is actually del of n minus 1. Okay, now hope you have an idea about that. Now what is this Fourier transform del of n minus k? You can again use the basic expression, n is equal to minus infinity del of n minus k e raised to minus j omega n. Now we know that. So how will you do this? Okay, we just want the value del of 0. Okay, at what value this n becomes equal to 0, or this part becomes equal to 0, that is at n is equal to k, right? So at n is equal to k, what happens to this signal? This signal becomes equal to 1, because this becomes del of 0. Del of 0 is 1. So this n also becomes k, that is the signal will be e raised to the function will be e raised to minus j omega k. But you can have a substitution method like this as well. You can do this in this way. Put n minus k is equal to p, n is equal to p plus k. So multiplying that, so you will get sigma. So as n varies from minus infinity to plus infinity, if you substitute here, p also varies from, so you put p instead of n, del of p e raised to minus j omega p into, you are splitting it up, right? So this is actually, instead of n, you can write it as p plus k. So that is minus j omega into p plus k, or you can split that as e into e raised to minus j omega k. Okay, if you have doubt, you may just combine this. You will you will be getting this. Okay, now what is this basically? This is basically equal to del of n into e raised to minus j omega n. Instead of n, you have a p. So the value of this signal, which we have already found out in this example, okay, this is equal to 1. So that means this is equal to 1. So the resulting is e raised to minus j omega. This is what we found out here. Okay. So that's about the shifted impulse signal. Then you have another u of n minus k e raised to minus j omega n. You know what is u of n. So this is actually your u of n. When you shift this u of n by 1 unit, that means this will look like this. Okay, shifting. So this will be 0. This is u of n minus 1. So what about the Fourier transform of such category of signal? This is also, since u of n is integrable, non-integrable, u of n minus k is also non-integrable. So what you need to do is, you are actually say substituting n minus k to p, or n is equal to p plus k. So that means the n varies from 0 to, it is not n, this is p. P varies from 0 to infinity u of p into e raised to minus j omega p. From this, when you substitute n to be p plus k, you can split this as e raised to minus j omega k. Now this we have already found out, right? This is equal to sigma n is equal to 0 to infinity u of n into e raised to minus j omega p. How do you find this? This is actually the Fourier transform of, this is actually the Fourier transform of u of n. But the Fourier transform of u of n is found out by multiplying this by a raised to n as limit a tends to 1. Using that, you will be getting this, right? So which, this is the thing which we have already dealt with, that is this. Okay, so this can be, okay, this can be this can be called as what? The Fourier transform of u of n. And the Fourier transform of u of n is already found out, that into e raised to minus j omega k. So that's the fourth one. Then you have the a raised to n into u of n. Okay, this sounds similar to the limiting function which we have just done. Anyway, this is another type of problem. A raised to n into u of n, that is just an exponential signal. Okay, this is a discrete exponential signal. Well, I mean, we know that if a is less than 1, I mean, every time it won't be a integrable function. When it is going to be an integrable function, since it is a raised to n into u of n, this is a positive going signal, and if the positive going signal has to be an exponentially decaying signal or a time limited signal, this n has to be, a has to be, what is the condition for the a? A has to be less than 1. What happens when a is greater than 1? For example, 2 raised to 1. So 2 raised to 0 is 1, then it starts, the next value will be 2, 3, and it goes on like that, right? So this signal can be either like this or this, like this. I mean, sorry, it is discrete. So it can be like this or like this. So when this signal will be like this signal will be like this only if a is less than 1, right? Now, so imposing that condition, so you can expand this as 1 plus a into e raised to minus j omega into this thing. So this is a geometrical progression with common ratio. What common ratio is a into e raised to minus j omega. What is the magnitude of this? Now we want to see that the magnitude of this is less than 1, but we know that e raised to minus j omega, it is 1, it is not less than 1, and for this quantity to be less than 1, the only possibility is a has to be less than 1. If a is only less than 1 only, then you can say that this converges to this value. Otherwise, it doesn't have a Fourier transform. So this is going to be the Fourier transform of an exponentially decaying signal. Suppose the question had been like this. Say for a greater than 1, find out the Fourier transform of this. You must write that Fourier transform does not exist for such signals, because what happens is when a is greater than 1, you are going to get a signal like this. This is a unbounded, time unbounded signal. That means for such signals, when you integrate or when you summate the whole samples, you are not going to get a finite value. Okay, so hence it is not summable. Okay, now the next question is okay, there is a change in number. Okay, let's call this as 5.1. Okay, now what about del of n plus 2 minus del of n minus 2? We have already seen, in this case, we have already seen what is del of n minus k. So del of n minus, the Fourier transform of del of n minus k e raised to minus j omega k. So what must be the Fourier transform del of n plus k? N plus k. Following this will be e raised to plus j omega k. If n minus k is e raised to minus j omega k, you can also prove that. You may do it as this is given as a exercise for you. Find the Fourier transform del of n plus k. You can prove this to be e raised to plus j omega k, that you are simply applying here. So this is del of n plus 2. Del of n plus 2 is e raised to plus 2j omega. Del of n minus 2 is e raised to minus 2j omega. That means what you are doing is you are actually finding out the Fourier transform of such a signal. That is, this is minus 2 and plus 2. Del of n plus 2, del of n plus 2 and del of n minus 2. So this must be del of n minus 2. This will be like this, right? Right, isn't it? So this is actually plus of minus, right? So this is 1, this is also 1, okay? So this is a kind of signal that we have, and when you find out the Fourier transform, you will get e raised to 2j omega minus e raised to minus 2j omega. Applying the Euler's relation, you can prove that this is to be 2j sine omega. So this is actually the Fourier, the frequency domain of this time domain signal is a sinusoidal signal, sine omega. Okay. Okay, now coming to the sixth one problem. So you are given with the x of n with the sequences 1, minus 1, 2 and 2. We know that this represents the 0th sample, this is the first sample, second sample and the third sample. So altogether you have 4 samples. Now in order to find the Fourier transform of this, you can use the basic expression n is equal to 0 to infinity, but you know that here n varies from 0 to 3. So n is equal to 0 to 3, x of n e raised to minus j omega n. Expanding, you get x of 0 into e raised to minus j omega 0 plus, you put n is equal to 1, 2, 3 and you will be getting this. So be careful about this. The term will be e raised to minus j omega 0. This one is e raised to minus j omega into 1. This is e raised to minus 2 j2 omega and e raised to minus j3 omega. Okay. Now from this you can fill this x of 0, x of 1, x of 2 and x of 3. X of 1 is 1. This is minus 1 plus 2 plus 2. Okay. Now this is actually your Fourier transform. That's all. So this is the discrete time Fourier transform of a given x of n sequence. Now you have another signal called as 0.5 raised into u of n into 2 raised to n into u of minus n minus 1. Now when you deal with such signals, first of all you should see this x of n is represented as some x1 of n into plus some x2 of n, right? Now first of all what you need to do is we need to check for the existence of Fourier transform of these signals, that means these two signals, right? Now we know that from our previous discussion 0.5 raised to n into u of n, that is sigma as n varies from 0 to infinity because of this u of n. This will be definitely a value less than infinity because what? Because it is half. So the first term will be 1, second term will be half, right? Third term will be 1 by 4. So as you see in this direction when you look, so the value of n increases, this term gets reduces and ultimately it will reach to 0. So anyway, so this is so that means this is going to be a geometric series, geometric progression it is. So you will be having a common ratio of half. So it will converge to 1 by 1 minus half. So that means this particular signal is summable, right? Now what about 2 raised to n into u of minus n minus 1? Will it be so? From where this n varies, since it is u of minus n minus 1, how will be u of minus n minus 1 look like? This is u of n minus 1, right? This is u of n minus 1, that is 0, minus 1, minus 2 up to n. So actually the signal ranges from minus infinity to plus infinity, right? Now when you put n, all this value of n is negative. So when you put that value, there will be a negative sign here, right? So negative sign here. So you don't have to change this. This will be anyway, the magnitude is 1. Okay. Now when you look at this, this is nothing but n is equal to minus infinity to minus 1 half raised to n, right? So it is again, no, this is exactly the same geometric progression you can see. So this is also summable. Therefore, so this is the first thing that you need to check. So you should say that the Fourier transform exists. Now what is the Fourier transform? This will be sigma n is equal to 0, 0.5 raised to n into e raised to minus j omega n. This will be minus infinity to plus. Okay, so this is it. Now you can substitute that. Substitute the value 0.5 raised to n. That is u of n is equal to 1. This will be 2 raised to n into u of minus n minus 1 is 1 e raised to minus j omega n, right? But the limit varies from minus infinity to plus infinity. Now you can change the polarity of or the sign of this limits, right? So you can change it from 1 to infinity, provided wherever you find n, you should replace that by minus n. So that means n is equal to 1 to infinity, so that this becomes 2 raised to minus n into e raised to plus j omega n. Now the next is, so this is 2 raised to n and 2 raised to minus n means 1 by 2 raised to n. So it is actually 0.5 raised to n. Okay, so this is nothing but this is actually 0.5 raised to n, as you can see here, right? As okay. Now you can expand this. So it will be on expanding, you will get, in this case you will get 1 plus 0.5 e raised to minus j omega plus 0.5 e raised to minus, and in this side this is half, right? Half into e raised to j omega. So this is a geometric progression of the form 1 plus r square, etc. But this is not in that form, right? But you can make that in the form by taking this half e raised to j omega common. So this also became a geometric series. So both are geometric series. Now what is the geometric progression? What is the sum of, if this is a common ratio, since because there is a 0.5, the common ratio is less than 1, so you can write that common ratio is 1 by 1 minus r. Okay, so similarly this can also be, this is also a geometric series with the half into e raised to plus j omega is the okay, whether it is e raised to plus j omega or e raised to minus j omega, its magnitude is 1, but because of this half, it is, since it is less than 1, you can converge, make this series converge to this sum as well as here. So now this is half into e raised to j omega into, so you can combine this together. So you can find out the LCM of this 1 minus 0.5 e raised to minus j omega. This is 1 minus 0.5 raised to e raised to plus j omega. Taking the LCM and applying Euler's identity, you will arrive at this answer. So you may do the rest of the steps by yourself as okay. Now the next one is to find out the IDTFT. Okay, now the question is to find out the IDTFT, meaning inverse discrete time Fourier transform of the following sequence. So what is the meaning of that? You will be given with x of omega, you have to find its corresponding time domain sequence. So that is the inverse of this discrete time Fourier transform. Now how to find that? Before that, when you are given such a question, first of all you may just try to draw that figure. So look at this, you have three ranges are shown. Now how to draw this? Anyway, what is actually the maximum range of the signal? So we know that from the expression. So let me just write down that expression. This is 1 by 2 pi integral minus pi to plus pi x of omega e raised to j omega n d omega, right? So this is the expression, right? So I have explained why this minus pi to plus pi, there is always a span of 2 pi, and the because x of omega is periodic with 2 pi, this always ranges from minus pi to plus pi. So there must be a span of 2 pi. Now you can just find out, you can just translate this representation in figure. Now what is this? This actually ranges from minus pi. So let us mark this minus pi and plus pi. Okay. Okay. So let us call this as pi by 4, this as pi by 2, and this one will be 3 pi by 4, right? 3 pi by 4 and finally pi. So what will be this? This will be minus pi by 4 minus pi by 2 and minus 3 pi by 4. Okay, so finally it is minus pi. So you may just try to draw it equidistantly. Okay, now what is this? What is the meaning of this representation? X of omega is 1 between pi by 4 and 3 pi by 4, meaning, right, this is it. Okay, but this omega, it is shown as modulus of omega. That means whether it is minus pi by 4 to minus 3 pi by 4 or plus pi by 4 to 3 pi by 4, the value is 1. So how will you represent that? This is not enough. So this will also represent like this. Do you understand the meaning of this? Because this is the magnitude. The meaning is omega can be both negative and positive. Whatever may be the value, that ranges from, so it ranges from minus pi by 4 to 3 pi by 4. Its value is equal to 1. Okay. Now let us see. 3 pi by 4 to, again, the magnitude of omega, if it lies between 3 pi by 4 and pi, that means this region and this region is equal to 0. And similarly, the regions between, this is the magnitudes, regions between 0 and pi by 4, that is also 0. Okay, so hope you understood this. So this is how you need to draw. Now this thing has become very, very simple. Okay, now let's see how is it. So this is equal to 1. Now then only you will be able to understand how to split up that integration. Okay, now what is your x of n? X of n is, okay, 1 by 2 pi integral minus pi to plus pi x of omega e raised to j omega n d omega. Okay, so you need to split up this because there is a negative interval as a positive interval. So anyway, in the negative half, the signal only starts from minus 3 pi by 4 to what? 3 pi by 4 to minus pi by 4, and in that case this will be, the value is 1, that into e raised to j omega n, okay, d omega, plus now all the rest. So minus pi to minus 3 pi by 4 is 0, minus 3 by 4 to pi by 4, minus pi by 4 is 1. Now minus pi by 4 to plus pi by 4 is again 0. Then you have from, yeah, pi by 4 to 3 pi by 4. This is 3 pi by 4, right? This is 3 pi by 4. It is again equal to 1 e raised to j omega n d omega, right? Now how will you write that? So this will be e raised to, now you can just integrate this. Integrating, you will get this as j omega n divided by n, right? So that is a 1 pi, don't forget to put this, 1 by 2 pi is common to all this. So this is 1 by 2 pi into e raised to j omega n plus, so it ranges from minus 3 pi by 4 to pi by 4 plus again you have here also, you will be getting e raised to j omega n by n, as n ranges from pi by 4 to 3 pi by 4. Okay, so you can just simply make a substitution for this omega. Okay, now you can take this 1 by 2 pi n outside. Okay, 1 by 2 pi n into, okay, so you can just make a substitution of this, that is, I'll just do that for you, e raised to j n pi by 4 minus e raised to minus j n pi by 4, 3 pi by 4, okay, n 3 pi by 4 plus e raised to j omega, sorry, e raised to j 3 pi by 4 n. So we are substituting for omega, okay, minus e raised to j pi by 4 n. Okay, now you can combine these together, right? E raised to j and pi by 4 minus e raised to j. So here it will be minus, this is minus pi by 4. Okay, so this will be minus. So you can combine this minus and minus. Okay, you can take the negative sign, so you can convert that into. Now you can apply what? Apply this. Apply the. Apply what? Apply. You can apply Euler's identity. So there will be an e raised to nj. Sorry. Okay, there will be a presence of j, and using all these things, Euler's identity, you can prove finally your answer as 1 by pi n into sine 3 pi by 4 n minus sine pi by 4 n. Okay, so this is it, minus 1 by pi n into sine 3 by 4 n minus sine pi by 4 n. So this is the inverse Fourier transform of this segment. Okay, now let's move on to this question, ninth question, which is find the inverse Fourier transform of x of omega. You are given with x of omega is equal to 1 plus 2 into e raised to minus j omega plus 2 into e raised to minus j2 omega plus 3 into e raised to minus 3 j omega. So when you are asked such a question, what you need to do is you can expand the general expression for x of omega. You know that this is sigma n is equal to minus infinity to plus infinity x of n e raised to minus j omega n, right? Now, so you should expand in such a way that let's start with the 0th sample and write on the left and the expand on the right side and the left side as shown. So look at this. When you put n is equal to 0, this becomes x of 0, this is e raised to minus j0, which is equal to 1. So x of 0 plus x of 1 into e raised to minus j omega, n is 1. So this will be x of 2 into e raised to minus 2 j omega and so on. On the left side, you will have x of minus 1 into e raised to plus j omega, e raised to minus 2 j omega and so on. Now, this is, so call this as equation 2, this was 1. So you can just compare this. Now we can see a constant term without any exponential signal. So that corresponds to what? X of 0. What you are going to find out is inverse. Inverse means you are finding out, what is the meaning of inverse? Finding out x of n from x of omega. So this is one way of finding out the finite duration sequence. Right. It is a method by which you find the finite. It is finite duration. So you can simply write the general expression and have a comparison on that. Now similarly, when you look at this expression, all these expression is having e raised to minus part. So e raised to minus part is on the right side of this. So you can have a comparison. So e raised to minus j omega, this term or this 2 corresponds to x of 1. Okay, since it is e raised to minus 2 j omega, x of 2 is equal to 2, x of 3 is equal to 3. So there it is written. So what is this? This is actually equal to, so your x of n will be, what is your x of n? X of n will be 1, 2, 2, 3, right? So this is how. So this is the 0th sample. Okay. Now the next question, that's the 10th question. So you have find the Fourier transform of x of n is equal to a raised to plus modulus of n. What's the meaning of that? A raised to modulus n. So first of all, what is a raised to n? This is actually the discrete exponential signal, and that's the major difference between the continuous exponential. Continuous exponential signal is of the form e raised to something, while this is any number. A can be any number. A is a raised to plus n. Now if this signal should represent this one, or if a raised to plus modulus n should represent like this, that is whether n is negative or positive, this will be modulus n. So it will take only the positive value. So a raised to plus n. Now if this signal needs to follow this, what must be your a? A has to be less than, right? Now if a is greater than 1, if less than 1, if a is greater than 1, then what happens is as n increases, that's going to increase in a increase, while this is due to the fact as n increases the signal decreases due to the fact that a is less than 1. Okay, so you must be very careful when you deal such problems. Okay, now if you are not imposing such a condition, you cannot have a signal like this. That will be a growing signal. So why this is a decaying signal? Because of a, because of the condition imposed by a is less than 1. Therefore, say for example, if you are having a half raised to modulus n, means in this side also, in this side also it will be half raised to, so if suppose if it is minus 1, half raised to modulus of minus n minus 1, that is modulus of minus 1 is 1 itself, so half. Here also you will get the same value, right? So that's how it is. Now to find out the Fourier transform, you want to find out the Fourier transform, you can use this straight away expression n is equal to minus infinity, and you are splitting it from minus infinity to minus 1 a raised to minus n e raised to minus j omega n. Why you have put a raised to minus n? When you put the negative values, this should become a raised to n, because a is less than 1, right? Similarly, in this case also it should be a raised to n, right? So you don't need to change the sign. Why you are changing the sign? Because during this interval n is negative, so when that negative comes along with this, it will be made positive. Suppose if it is a minus 1, what happens? When you put half raised to minus 1, which is equal to 2, so that means that particular value becomes greater than 1. That means subsequently as n increases, what happens? This increases. So during this interval, this modulus must be replaced by a raised to minus n. So this is the basic thing which I am speaking. So you might be understanding that. If you have any doubts, you may just refer your +2 mathematics books, how to change the integration limits and so on. Okay, now that means this is equal to e raised to, now you can change this summation from 1 to infinity. So what must be done? You must replace every n by minus n. So when you put that, it becomes a raised to plus n into e raised to plus j omega n. Here also e raised to, and since it is n is equal to 0 to infinity, you don't need to change that. So this will be thus. Now since a is less than 1, both these cases, this is going to be a geometric series. No, so this is equal to, say so as you as you put values for n is equal to 1 here, you will get this as e raised to j omega plus a into e raised to j omega 2 plus a square. Okay, a cube into e raised to j omega 3, etc. Okay, then plus, so this is how it works. Now plus, what about this? This will be, the first term will be 1 plus e raised to minus j omega plus e raised to, this is plus, right, e raised to minus j2 omega and so on. This is how it expands. Now we know that the value of a is less than 1. Therefore, now if you take this a into e raised to j omega outside, a into e raised to j omega outside, this will be 1 plus a into e raised to j omega plus a into e raised to a square into e raised to 2j omega, etc. This will be the same thing. Okay, now this is actually a geometric series, right? Geometric series with a common ratio r is equal to a into e raised to j omega. Now if r is, modulus r is less than 1, you can write this or substitute this as 1 by 1 minus r. Now the question is r is less than 1? Because a is less than 1, this value should be less than 1. Therefore you can write this expression as, or this geometric series as 1 by 1 minus a into e raised to j omega. Similarly, what about this? This also you can write in this way. Okay, here also you have right, a into, okay, 1 plus, this will be 1 plus a into, this is a square and so on. So here also you have a into e raised to minus j omega, because of the limits of, and because a is less than 1, this is also, this can also be written as a into e raised to minus j omega. Okay, now you can, so you will be getting that like this. So here you have a into e raised to j omega outside, so you will be getting this signal like this. Now take the LCM and you may do the necessary manipulation to arrive at this result. So you may do that rest of the work by your own. Okay, so that's the 10th problem. Now coming to the 11th problem. obtain the impulse response of the system as shown. Okay, now how to find the impulse response of the system, which is given as h of omega. So what is this h of omega? H of omega is actually equal to what is that? H of omega is the system function in time frequency domain. So in another sense, you can say that this is actually the Fourier transform of the impulse response. So how will you find out the impulse response? If you are given with the Fourier transform of impulse response, in order to find the impulse response, that is h of n, you need to find out the inverse. So this is a problem of inverse. So question can also be asked in this way. Okay, so this is basically, the question is basically to find out the inverse of this. Okay, since it is given as h of omega is equal to 1. Now how will you plot this? As I already told you, especially when you find the impulse, especially when you find the inverse Fourier transform, you should draw the spectrum first. So this can also be called as a spectrum or the Fourier transform first. So h of omega is 1, right? The modulus omega is be it minus omega c and plus omega c. Over this range, the magnitude is always equal to 1. And what about omega c up to pi? That is the values in between. So this means the values in between omega c minus omega c to plus minus pi and omega c to plus pi is equal to 0. Okay, so this is it. So you are getting a rectangular frequency domain signal. Now you are asked to find out, so this is your h of omega. We know that why this h of, and the speciality of discrete time Fourier transform. So this is actually the discrete time Fourier transform of a h of n. Now this discrete time Fourier transform is continuous in nature. That's what it shows, right? Now that we have already proved and we have studied. Okay, now how to find out h of n? If your h of omega is given, you can use the basic expression. What is that? 1 by 2 pi integral minus pi to plus pi 1 into e raised to minus j omega n. So here we can see that the signal actually ranges from minus omega c to plus omega c. So you can change the limit to be, it's not minus pi to plus pi, even though the expression is like that. So this is why minus omega c to plus omega c, because there is only signal over this range. So okay, now you can see it is a simple thing. You can simply do the integration. You will get e raised to j omega n as limit varies from minus omega c to so this is when you integrate this, you will get this as 1 by jn. It comes here, and this 2 pi 1 by j and 2 pi. Now this 2 and j you can take along here after applying the limit. So this will be e raised to plus j omega c n minus e raised to minus j omega c n by 2j. So you can combine this as sin omega c n by pi n. Now what I did is, you multiply and divide by omega c in order to make this same in the denominator and the numerator. So omega c is multiplied in the denominator and numerator. There is no problem in that, so that you can change this into a zinc function, right? A zinc time domain signal. Okay, so understand that a rectangular shaped DTFT has a zinc time domain signal. Okay, has a zinc time domain signal. That means now the next problem that we are going to prove is, if you have a rectangular discrete time signal, then the discrete time transform is going to be a zinc signal, and that is the duality property of Fourier transform, which we have already seen when we dealt with the continuous time Fourier transform.